candidates. Good afternoon.
Good afternoon, sir.
As you've been told, my name is Mr. Mulegi. I teach chemistry. I also teach mathematics. And I've also had the privilege of marking this subject called chemistry, paper 2, for quite a long time. During my experience as an examiner, there is one thing that has come out very clearly as to why students don't do very well in this subject called chemistry. And one of them is because candidates fail to answer questions as expected by the examiner. A question is set, you don't take time to understand it, you start answering. What you might be answering can be correct chemistry, but it has been misplaced. It's not the correct response for that particular question. Therefore, you end up performing poorly. And maybe when I look at last year's KCSE, that is 2019, when I say last year's, we know 2020 was a mad year. So we are talking about 2019. The candidature in this subject, chemistry, has been growing over time. In fact, as we talk now, it is almost becoming compulsory in all the schools. Most of the schools will prefer having chemistry done by most of the students. Like during that year, we had a candidature of around 691,802. Those are the students who sat for this subject called chemistry. And when you look at the performance was not very good because the mean, if you have a mean of around 18 out of 80 in chemistry paper 2, that mean is actually below what we expect. However, if you are a candidate who is preparing for this exam, you should look at this mean positively and say, if you are experiencing any challenges as far as chemistry is concerned, you are not the only one. There are so many other students who are going through the same, and that one makes it easy for you to even pass the subject. I'm very sure all of you take mathematics, and when we say the mean is 18, the mean means that most of the students in the country are just scoring around 18. We do measures of central tendency in mathematics. So the score are clustered around 18. So if you are a candidate and you are preparing, so long as you can be able to tackle some questions and score marks, then you'll be on your way towards passing chemistry. And let me also remind you that even those boys and girls who get A's in chemistry, is not that they get 80 out of 80. They don't score 80 out of 80. It is not possible for you to score everything. So if you are attempting a question and you discover, for one reason or another, you are experiencing some challenges, that one should not discourage you as a candidate. In fact, it should energize you to think and even perform better in those questions that you are very, very sure of. Now, as you prepare for your forthcoming exams, there are few things we expect you to have done as a candidate. You have been taken through the syllabus by your teachers, and I want to believe that you have been attentive. Because when I look around, I can see very attentive girls, and that is very encouraging. So I want to believe that all along, you have been quite attentive during the chemistry lessons. I also want to believe that in the course of learning chemistry, you have written good notes. When you fail to have correct notes, it makes your revision very difficult. And when you say writing your own notes, there are some students who form this habit of picking books from those fellows or their colleagues who are ahead of them and inherit those notes and decide to use the same. If you find yourself doing that, you actually disadvantaging yourself, because you can understand your notes, your own notes better, especially when it comes to summary. So I want to believe that as we continue preparing, as the exam continue approaching, as a candidate, you must have written good notes, notes that are going to assist you as you revise. And part of the preparation is that you must also attempt to interact with as many questions as possible. The past paper questions. For example, you can say, you can even say, I want to go through questions for the last 5 years and ensure that I'm comfortable in answering all of them. The importance of doing that is building confidence, building the correct speed, because this exam is normally timed. When you are given an exam and the duration is 2 hours, you're expected to score a maximum of 80 marks. It means that if you do it mathematically, you must know how many minutes are you supposed to spend in making 1 mark. That's why we say, as candidates, try as much as possible to interact, to attempt as many questions as possible. We have these books, a revision book like Chemistry Made Familiar. It has got so many solved problems, which I normally find useful to the candidates, especially when you are reading on your own. You can be able to look at how a question has been framed, then look at the answers. Look at how such a question is supposed to be answered. And that's what we call the solved problem approach. It can really help you as a candidate. You look at the question, just read that question, then look at how that question is supposed to be answered. That will also assist you in building that confidence. It will assist you in ensuring that your speed will not let you down. You may have a lot of content as a candidate, but if your speed is low, you will not be able to communicate with the examiner the kind of content that you have. So as you prepare for this coming exam, make sure that you look at your speed as a candidate. Are you able to finish the exam within a stipulated time? Then, of course, we expect you to have confidence. This exam is prepared to make all of you pass. It is designed to ensure that despite our varying abilities as far as learning is concerned, all those challenges are somehow taken care of in that examination. And that is why we have something we call the Bloom's taxonomy, which is supposed to ensure that all levels of testing have been taken care of. And this one being a national exam, it is done by experts. They ensure that it takes care of all those levels. Now, in the Bible, we normally say that it's written that God will bless the work of our hands. And all of us expect some blessings. So as a student, if you don't work hard, if you don't work, then God will have nothing to bless. Prepare ourselves for this forthcoming exam, and I'm very sure that we are going to do well. Now, as far as chemistry is concerned, unlike in some subjects where they say paper 1 is testing this area, paper 2 is testing that area, and paper 3 is testing something like that. In chemistry, when you are preparing for paper 2, we expect you to prepare. It can come right from Form 1. We have had questions testing Form 1 work, like when it comes to separation of mixtures, that is Form 1 work. We have had questions testing Form 2 work, Form 3 work, and even Form 4 work. So when you are preparing for this exam, prepare widely. Look at your Form 1 work, make sure that you polish it. Look at your Form 2 work, make sure that it is polished. Form 3 work should be polished, and Form 4 work the same. There are certain areas that are very crucial as you are preparing for the exams. The first area I would want to mention is the periodic table. The periodic table, and that one is done in Form 2. It's done in Form 2. The periodic table, some people normally call it the backbone of chemistry. The backbone. As a candidate, take time to understand the periodic table. You are advised to internalize this periodic table as much as possible. When you talk about the vertical columns, those are groups. The horizontal rows, those are periods. You must be able to know the trends as you move down the group, the trends in properties as you move across the period. So I'm advising you to take time and internalize the periodic table. Why am I talking about the periodic table? Once you know the periodic table, you'll find it easy, when you are writing chemical formula. Because of the valencies, you need valencies. When you talk about sodium chloride, unless you know that the valency of sodium is 1 and the valency of chlorine is also 1 from the periodic table, you'll find it difficult to write the correct formula of sodium chloride. So the periodic table will assist you in writing formula of compounds, and that one will follow you all the way up to Form 4. Because when it comes to the mole concept, you also need to know how to write the formula of compounds. When it comes to rate of reaction, it follows you all the way to Form 4. So I'm saying, let us take some special interest in understanding the periodic table, and you'll be very safe. Another important area which most of the students take lightly is this topic called salts. Salts. In Form 2, we do salts. That's where we talk about methods of preparing salts. And you must remember that the method we use here depends on whether the salt is soluble or insoluble, isn't it? So the moment you know that, which salts are soluble. And there's a salt we normally sing at that level. And we get comfortable that our students have internalized it. But as they move towards Form 4, they tend to forget which salts are soluble, which ones are not soluble. For example, nitrates. We normally say all nitrates are soluble. What about chlorides? What do we say about chlorides? And I want to request that we make this forum as interactive as possible, isn't it? So when we talk about chlorides, what do we say about chlorides? A volunteer. You want a volunteer, please? Yes? Very good. Can you appreciate her? Thank you very much. She's saying that all chlorides are soluble except lead chloride and silver chloride, isn't it? However, lead chloride is soluble in warm water. That's very good. What about carbonates? What do we say about carbonates? Yes? Except? Group 1 elements and ammonia, isn't it? Very good. Thank you. Appreciate her. All carbonates are insoluble except those ones of group 1 and ammonia. That's what you're saying. So, from the two responses, I'm satisfied that these students understand solubility of salts. That one I'm satisfied and I'm convinced. And in case we have one or two who are not very sure, we still have an opportunity of doing what? Revising, isn't it? So what I'm saying is it is good for you to understand that concept. Because once you understand this solubility of salts, it will follow you. It is even repeated in Form 4 as a serious topic. And when I say a serious topic, it's a topic that is normally tested in paper 2, and it can come with a lot of marks. So solubility, let us take it seriously. Another area you are not supposed to play around with is the reactivity series. The reactivity series. The reactivity series. The reactivity series. You should be able to arrange these elements in order of decreasing reactivity. Maybe starting with the most reactive up to the least reactive. If you are armed with that kind of information, whenever a question comes, if it's a displacement reaction, you are given a solution containing copper 2 ions. Somebody gives you a solution containing copper 2 ions. Then your zinc powder is being added. Then somebody is asking you, state and explain the observation made. State and explain. If you have understood reactivity series very well, I'm very sure when you finish reading that question, you'll find yourself smiling. So let us take time to understand the reactivity series. It will help us a great deal. And also the mole. The mole. What we do in Form 3, the mole. Now this mole, the mole, if you approach the mole from what we call the first principles, our teachers will guide you on what we mean by the first principles. You understand the mole from the first principles. Questions dealing with the mole, those questions are just repeated. How many moles? What is the molarity? What is the volume? Those questions are just repeated. Repeated. So if you know how to calculate concentration. You know, we have already said that from the periodic table, we must arm ourselves with the skills of writing stoichiometric equations. And you know, when I say a stoichiometric equation, what am I talking about? When you're in Form 1 and 2, we allow the use of word equations. And the reason that one is allowed is because you have not mastered the chemical symbols, isn't it? Then the chemical formula. So you are being given time to internalize those concepts. But the moment you move to Form 3 and 4, in Form 3 and 4, there is no room for word equations. When you are asked to write an equation representing a particular reaction, that equation must be stoichiometric. Stoichiometric. So what do we look for? The reactants, isn't it? On the left-hand side, we want to see the correct formula of the reactants. On the right-hand side, we expect to see the correct formula of the products. And then, the equation must be balanced. After balancing the equation, we expect to see the state symbols. So the moment the equation you are writing meets that criteria, that's the only time it can score a mark in chemistry. I'm going to use some examples. As we move on. Now, one of the challenges we have had with the candidates is actually the language. They have the content, but the problem comes in with the language. Now, you will allow me just to highlight some of the words that are very common, that are used by the examiners, and how you are supposed to interpret such a word whenever you come across it. Now, the first word I want to talk about is identify. Identify. Now, if you want to identify something, just allow me to use you as an example. Can you stand up? Now, supposing stand there, please. Now, supposing I want to identify this candidate of ours. I tell you, identify this candidate. How can you identify that candidate? A volunteer, please. Yes? You can look at the height. You can look at the height. So when she says the height, so she has looked at a certain property, isn't it? That is associated with this candidate, isn't it? So you can use the height. Thank you. What else? Yes? The name. Thank you. Isn't it? We can also identify her using her name, isn't it? We can identify her using her name. Thank you. Sit down. So, when a question says identify. For example, maybe I'm reacting magnesium. I'm reacting magnesium with hydrochloric acid. This is a metal reacting with an acid, so we expect it to give us a salt and hydrogen. So the salt should be magnesium chloride plus hydrogen gas. Very good. So I ensure that, is this equation stoichiometric? Supposing you are told to write an equation for the reaction between magnesium and hydrochloric acid. Then you write and leave it there. Will this question score? It will not score, isn't it? Because it is not balanced. So any equation you write, for you to start counting any mark, you must ensure that the equation is balanced. So how do we balance? I put a 2 here, isn't it? Now, most of the time, the question, writing equations, maybe it would be 1 mark. So if this one was 1 mark, 1 mark. If that is 1 mark, if you remove these 2, the equation is not balanced. So this one, you score a 0. Okay? You score a 0. Any equation that is not balanced. If you go ahead and put here a 2, now the equation is balanced, isn't it? But there is something that is not there. What is missing? The state symbols. So if you leave it there, you will not get the full mark. You will get a maximum of a half. Why? Any wrong state symbol, in fact we normally say wrong or missing. So if you forget all the state symbols, all of them, that's a half a mark. If you write the state symbols, this one is a solid, this one is aqueous, magnesium chloride, aqueous, and hydrogen is a gas. If you write like that, you are sure of the 1 mark. Supposing you make a mistake and say hydrogen is a solid, this state symbol is wrong. Therefore, you'll be penalized a maximum of half a mark for any mistake you make around the state symbols. So ensure, and let me tell you, in an examination situation, even that half a mark is very important. Because several halves, when you put them together, that is what makes the candidate to pass. And if you keep on losing half, and you lose so many halves in that examination, you'll end up failing. So, I was talking about identification. Now, somebody can tell you, I can ask you a question, identify the gas produced, isn't it? Identify. So if the question is identify the gas produced, we have said you can identify the gas by giving the what? The name. So you can say the gas produced is hydrogen. You have identified the gas. The way she told us that we can identify her using her name. So we have identified this gas using the name of the gas. That is correct. You can also, she said, you can look at the height. So you can look at a property that is associated with the gas. But in this case here, we can also identify it by giving the correct formula. Because this one here, when you see H2, as far as chemistry is concerned, this H2 cannot be anything else apart from hydrogen. So when a question says identify, this is what I want you to understand. You can either, what I'm emphasizing is, if it says identify, you can either give the name or the correct formula, and you should underline the word correct formula. If you come and say H, like that, this is not hydrogen gas. This is an atom. So the formula must be correct when you say identify. Identify. Now, still on the same. So we have said when the word identify has been used. Let me use the same case now to say, supposing now the person give the name. It says, give the name. Give the name. Give the name. Give the name of the gas produced. Are you getting what I'm saying? Give the name of the gas produced. What is the answer there? Hydrogen. The word hydrogen. This one now, has got only one response. You know? This one was a bit open. It had two possible answers, either the name or the correct formula. But when a question says, give the name, and you come and write 82, this one here, you'll do what? You fail because you have not given the name. You must write the word hydrogen. Still on the same, the examiner can now say, write the formula of the gas produced. Write the formula. This one is also specific. Yes, this one is also specific. Write the formula. So when they say write the formula, then there is no, you don't have any other way out of it apart from writing the formula. Okay? Apart from writing the formula. Another common terminology we have, I want to use this one to make reference, to make several references, so that because it can explain what I want to put across. Suppose, still on this reaction, you are asked to state and explain the observation made during this reaction. State and explain the observation made. How many questions are those? Those are how many questions? Those are 2 questions. And those 2 questions are tied. State and explain. You must first of all make the correct statement. You must score for the statement before you score for the observation. If the statement is wrong, for example, state and explain the observation made here, and you say the solution turns from colorless to black. That is not true, isn't it? So even if you go ahead and explain that hydrogen gas is being produced, that one you have already spoiled. So when a question says state and explain, look at it as if there are 2 questions. 2 questions. You must, there's no way you can score for the explanation if the statement is wrong. However, if you state it correctly and explain in the wrong manner, you will score for the statement. So when a question says state and explain, like here, if you wanted to answer that one, I want us to answer that question together. State and explain the observation made during this process. I expect an answer from the floor. You might say yes. Bubbles were observed. Bubbles were observed. That's what she has said. Is she right? Bubbles were observed. So she has said, bubbles were observed. She is correct, isn't it? Very correct. Bubbles will be observed. Any other answer? Yes? Effervescence, isn't it? So bubbles are observed. That is correct. Effervescence is also correct, isn't it? So the observation, bubbles. Supposing somebody says, as an observation, a colorless gas is produced. Is that correct? What makes that statement wrong when you say a colorless gas is produced? Yes? Pardon? Yes. A colorless gas is invisible. You cannot see it with your eyes, isn't it? You cannot see it with your eyes. You cannot observe the gas hydrogen. You can only see it in form of bubbles. So when you say the observation is bubbles, or if you say bubbles of a colorless gas, That is still right, isn't it? Because of the word bubbles. Bubbles can be seen. When you say effervescence, that is still correct as an observation, isn't it? Now, what do we give for the explanation? What do we give for the explanation? Yes? Yes, correct. Hydrogen gas is being produced, isn't it? That's why you are seeing bubbles. Hydrogen gas is being produced, that's why you are seeing bubbles. And you see, when you look at this chemistry, though chemistry is a subject that we apply in our everyday life. I remember it's around 2 years back, there was a very simple question, but I was surprised with the performance in that particular question. Because the question was, state and explain when a bottle of soda is opened. What will be the response? Just to check, paper 2. Yes? There is effervescence, isn't it? That's correct. There's effervescence. That's correct. There's effervescence. What will be the explanation for that effervescence? Yes? Carbon dioxide is escaping, isn't it? Yes, it's carbon dioxide. This is chemistry we have done during the manufacture of soda. We know why carbon dioxide is dissolved in that water, isn't it? Yes, we know why it's dissolved. So when you're opening, the gas that was dissolved is escaping. So how will you know? Will you know that this gas is escaping? When there is effervescence, isn't it? When there is effervescence. Another way of putting it, because we can give different answers, but we are talking about the same thing. Another way, apart from effervescence, you see when you talk about observations, remember observations, we expect you to make use of your eyes, even ears. Yes, even ears. So supposing I guide you, if you're opening a bottle of soda and you're using your ears, what will be the observation? Yes? A what? A hissing sound, isn't it? You can hear a hissing sound. Yes, that's correct. What causes that hissing sound? Because you have said state. So the statement is a hissing sound. What is the explanation for the hissing sound? What's the explanation? The hissing. The hissing. It is still related to the first answer, isn't it? Yes. When it is hissing, what is producing the hissing sound? The carbon dioxide that is escaping, isn't it? Yes. So if you say a hissing sound is produced, that's an observation. What do you write as an explanation? Carbon dioxide is escaping. And the same question, still on the same, there's a year when they asked you to state and explain what is observed when a piece of sodium metal is dropped in a trough of water. State and explain what happens when a piece of sodium metal is dropped in a trough of water. Yes. Was not attempted. I want more participants. Yes? There is effervescence, isn't it? Are we in agreement there is effervescence? Yes. What causes this effervescence? State and explain. What causes it? Huh? Production of hydrogen gas. I hope you are getting the point I'm saying. If your answer is effervescence, what causes the effervescence is the production of that hydrogen gas, okay? Apart from that, what else can you hear as an observation? Hissing sound, isn't it? So what is the meaning of that hissing sound? the hydrogen gas produced is now escaping, isn't it? The gas that is produced is escaping. That is why it produces a hissing sound. So what am I saying, our candidates? When a question says state and explain, look at it as if those are actually two questions. Those are two questions, and you must be careful with the statement. The first statement you make should be correct for the answer to be acceptable. Now, there are times when you are asked to state laws. In chemistry, we have laws. We have Boyle's law, we have Charles' law, Graham's law, score marks on the graphs. And it's very easy so long as you do the right thing. The first thing you are supposed to be careful with is the scale. When you have been given the graph paper, if this is the size of that graph paper, you must choose a scale that will ensure that when you are plotting, you make use of more than 3/4 of the graph paper. Some students, you have been given this graph paper, but when you plot your graph, it's just something in one corner, like that. This one will mean that there's a problem with line. If it's a curve, that curve must be smooth. When we say a curve is smooth, if you have points, like that. Now, the moment you start joining the points, you should not break at all. You should not break at all for that curve to be smooth. Supposing you break somewhere, you join up to here, you stop. You decide to sharpen your pencil, then you continue. That curve will not be smooth. Therefore, the mark for the curve will disappear. The mark for the curve will disappear. If it's a straight line, we even do it in mathematics. You are drawing and you discover that these points are suggesting a linear relationship. They appear as if they are lying on a straight line. When you observe that, then you must use a transparent ruler to draw what we call the baseline of fit, isn't it? We know how we do it in mathematics with a transparent ruler. So, like that. So if it's a line, let it be a straight line drawn using a ruler. If it is a curve, let it be a smooth curve, depending on the data that you have been given. Now, another thing you're supposed to know, especially when you're talking about maybe it's neutralization. Neutralization, you are reacting sodium hydroxide. Sodium hydroxide is reacting with hydrochloric acid to give us sodium chloride plus water. Aqueous, aqueous, aqueous. Water is a liquid. And as you write that equation, don't forget what you have said about equations. Now, this reaction is exothermic. It produces heat. So when you are doing it, if you are supposed to draw this graph, you will discover if we had, if on the y-axis we have temperature, and here we have time. When you plot this graph, you will discover that the temperature will increase. A time will come when it starts doing what? Decreasing. Like that. Now, when you are asked now to determine from your graph the highest temperature, we expect you to do what is called extrapolation. You join using a ruler, like that. You come and join this one. Where the two meet, that is what you're supposed to use as your highest. You extrapolate. This is a skill that has been disturbing our candidates when they are writing the exam. They fail to extrapolate. When you say the highest temperature, they just come and look at where, if it's a curve behaving like that, most of them give this one as the highest temperature. That's not right. You must extrapolate. You must extrapolate. And still on the scale, another thing you're supposed to know about the scale, your scale must be linear. Your scale must be linear. When you say linear, it means that if you have started from 0, maybe you want to use 10, 10, 10. So it should be 0, 10, maybe 20, 30, 40, 50, uniform. But if you decide to start with 0, then you come and say, the next box you say 10, then instead of 20 you move to 30, then from 30 you move to 35. This scale, we say it is not linear. And it will not score for the mark of the scale. However, one thing I also want to tell you is that questions dealing with the graphs do not have predetermined answers. The answer is what you are going to give, so long as you are obtaining it from the graph. So you can make a mistake even with the scale. You can make a mistake with the scale and be penalized for the wrong scale. But if you plot correctly using the wrong scale, that one will still give you full marks for the plots. If you join correctly the plotted points, if it is a curve, we see a smooth curve, you will get full marks. And then you are supposed to use that graph to answer certain equations. So long as you are reading these values from the graph that you will have drawn, the graph will be wrong, yes. But because we are penalized at the level of the scale, it will not be penalized again. And that is what we normally call now consequential marking. Consequential. And that one applies to even calculations dealing with the mole. When you look at those calculations, you can have a situation where you have part A, for example, is asking you find the number of moles. This is A. Part B, find the molarity. Part C, maybe find the concentration, something like that. Maybe all these parts here, part A, part B, and part C, for you to answer, maybe you are required first of all to write a balanced equation. And maybe at the beginning, you were unable to balance that equation. So you wrote a wrong equation. So if you wrote that wrong equation and failed to balance, of course at that level, you will be penalized for the wrong equation. However, if you continue using that wrong equation and you use it correctly, your answers will be different. The answers you are going to get will be different, but they will be scoring full marks. And that's what we call consequential marking. Marking based on what the learner is doing. So that's why you must always have a calculator. We look at learner A. He used this value. Go to this answer. So the questions dealing with the graphs do not have predetermined answers. It is you to do the correct thing and you get the marks. Is that clear? Yes. So I want to believe that this is just the start of so many other interactions, and I'm guided not to continue forever, but to give you an opportunity to ask questions, if there is any, so that we can have more interactions. Maybe, yes. So I kindly request that if you have any question, any area that you think you need some guidance, you are free to do so within how many minutes, my director? at most 30 minutes. So we have been given at most 30 minutes to listen to any questions so that we can even share. I've not exhausted everything because of the time factor. At the same time, we might be having different challenges as candidates. So I'm requesting that if you have any question, you just carry up your hand, you'll be given the microphone, you ask so that we can be able to share for the purposes of all of us learning. Remember, learning is a continuous process. I'm also learning from you as you learn from me.
Right, so let us take the first set of 3. We are going to go in sets. Okay? So ask one question, another one question, 3. Then answers those, then we get another set.
I want Adam to assist me.
Oh, okay.
On graphs of rates of reaction. The graph on rates of reaction. The scale, the standard form, how we use to plot the plot on the graph of rates of reaction.
When you are asked about to state the condition in the organic chemistry, what do you state?
The 2017 practical that was done, it was the students are supposed to write the procedure of to write their own procedure. So my question is, if you fail in the start, maybe your first procedure, are you going to lose all the marks? Will it affect all the marks of the testing?
Thank you for the first 3 questions. Maybe I beg to respond. Now the first one is about the scale, especially when you are, there are times when you find yourself dealing with maybe very large values or very small values, especially maybe the time you timed in microseconds or seconds, minutes, something like that. Now you see, what we are saying is this. If you have values like maybe 2 times 10 raised to power 3, another one is 3 times 10 raised to power 3, another one is 4 times 10 raised to power 3. Now you see, or even negative, let me even use negative like that, show that they are very tiny values, isn't it? So when you are choosing your scale, suppose you want to put these values on the y-axis or whichever axis. What you do? Times 10 raised to power negative 3, isn't it? Times 10 raised to power negative 3. So once you have done that, you just look at them. 2, 4, 3. This one becomes very easy now. So that if you start here with 1, this one is 2, this one is 3, this one is 4, 5, like that. So you have simplified. So anybody looking at your value, when this person sees a 1, the person is aware. You have guided the tell her that it is 1 times 10 raised to power negative 3. So that you don't have very small values here. You don't have decimals here. Let's tiny values to plot. Then, still on the same, you may discover that the values do not necessarily start from 0. They don't start from 0. Maybe you are doing an experiment, and here, this is time, and maybe time, and here we can have maybe mass. So that time is 0, maybe mass is 1,000. Time 1, maybe mass is 800. Time 2, mass is 600. Times 3, mass is maybe 500. Something like that. Now you see, when you are drawing now, then you are asked to draw. You are asked to draw mass, a graph of mass against the time. So what will you have on the y-axis? The mass, isn't it? Now, when you look at the mass, so you draw your axis like that. We have no problem with the time, because time starts from 0. So 0. Now, before we do that, look at the values on the y-axis. The values on the y-axis, the smallest is what? 500, isn't it? So if I'm not careful with the scale here, the 500 the smallest value might be somewhere there, and the largest value can easily go beyond the grid, isn't it? So that's why we are saying it's not a must that you start from 0. However, you must be very careful with where you place. For x-axis time, I can start from 0. But for the y, I don't start from 0. So, if you put a 0 here, what does that one mean? If I put a 0 here, look at where the 0 is. It has a meaning. This 0 is affecting both x and y. So if I put a 0, then I expect maybe here I say 1, 2, 3, 4, 5. Okay? And if I put a 0 here, then the next value, I should put a value that will show that this scale is also linear. So if I can put a 0 here and I come and say 500, maybe 600, 700, and I continue 800, this one is wrong. Because from 0, I've jumped to 500. However, you can cure that so that these values can be plotted. So if you want to cure it, just move this 0. This 0, move it so that you put it on this line. When you put it there, it means that it's only the x-axis, not in between. Then this one, you can do what? You break. You can break so that it's not a must. Or alternatively, you can as well move. It's not a mistake for you to come and say, it's not a mistake for you to say, you draw it like that. This is 0, 1, 2, 3, 4 at the x-axis. Then for the y-axis, I can just come and start with the 500 here. That's not a mistake. The 500, then I continue. Like that. So you can play around with the breaking of the axis, writing in standard form, and you see, like in chemistry, if you are talking about a solubility curve, you'll have been given maybe the solubility of a certain salt, solubility, and the temperature, in a table. Then they tell you to draw a solubility curve. Solubility curve, a graph of solubility against temperature. Solubility against temperature. So if they have already told you, draw a graph of solubility against the temperature, it's not a must for you to come and write here what? Temperature, and here you write what? Solubility. It's not a must. Because it is already in the stem of the question. The question has told you solubility against temperature. So whatever we see on the y-axis, we take it to be solubility. Whatever we have on the x-axis is temperature. Is temperature. So just play around with the values so that you can come up with what you can plot very easily. If it is in standard form, just write somewhere, maybe times 10 raised to power this, then the rest become whole numbers. It becomes easier to plot. There's a question that was asked about, that's in organic chemistry, where we talk about condition, reagent, and the type of reaction. Now, allow me to use this one as an example. Maybe the reaction of alkanes with halogens. For example, if it is methane reacting with chlorine. So, then this one here gives us CH3Cl plus HCl. Now we know very well that this reaction requires some energy to take place. No? That's why we say it cannot take place in darkness. It must take place in the presence of light. And we look at light as a source of energy, isn't it? Yes. Light is a source of energy. So here we normally write UV light. No? UV light. So when we talk about the condition we are looking at the environment. How should the environment be? The environment, so this is the condition, and say this is UV light. No. Type of reaction, I'll call it substitution. No. Substitution. Process. What is the process? Name them. This one, they normally follow one another. 3 type of reaction, condition, process. Yes, if you say halogenation, that is right. No, because chlorine is a halogen. You can say halogenation, or specifically chlorination, because you are adding chlorine. Another example is like when you are carrying out dehydration of ethanol, you want to convert it to ethene. So this is CH3, CH2OH. Then to give us, so here we have H2SO4 liquid. To give us CH2, plus water. Look at that reaction. And remember, you must be careful to say that sulfuric acid is a what? A liquid. Okay? A liquid means that it is concentrated. Supposing you say aqueous. Will the reaction take place? No, because the dilute sulfuric acid does not have that dehydrating property. So it should be liquid. Supposing you don't commit yourself about whether it's a liquid or aqueous, what happens? If you say liquid, correct. If you say aqueous, wrong. What about if you don't write anything? You just write H2SO4. What happens? Wrong. Or right? are right. Because what is going on in your mind is, did this student mean dilute or concentrated, isn't it? That's what you're saying I have. Huh? Did he mean or did she mean dilute or concentrated? When something like that happens, when the examiner is doubting what you are talking about, the benefit of doubt will go to the candidate. So here, if somebody writes H2SO for liquid, that's the correct thing. If you write H2SO for aqueous, you'll be penalized for what we call a wrong commitment. But if you leave it like that, you get what we call benefit of doubt. Now here, for this reaction to take place, what else is required?
Temperature.
Temperature of what? 1? 1? Very good. 160 to 180. 160 to 180. So, 160 to 180. So if somebody now, we are talking about name the conditions. Give the conditions. Give the conditions. One thing you are supposed to ask yourself before you give the conditions, what is the role of this sulfuric 6 acid? Because if it was reacting, if sulfuric 6 acid was a reactant, then it should appear on the side of the product. See, no? But it's not appearing anywhere on the side of the product. Therefore, this one, because it is regenerated, if you write the equation properly, systematically, this sulfuric acid is produced again. So because of that, we look at it as playing the role of recovery. So if you make a mistake in the first place, then you show that you have recovered from that mistake. You cannot really be penalized. That is why, and that question is related to paper 3. And as you prepare for that paper 3, you'll discover that in your practical work, we don't have like, if it is titration, we can have, if you are 100 students here, we can have almost 100 different answers. But all of them will be right or wrong depending on how you use the values. Because when you're doing an experiment, there is that aspect of experimental error that comes in. We are using different apparatus, so there's no way we can get the same values. However, if you use the values correctly, you cannot be penalized twice. So if, for example, you are performing an experiment and the correct value you are supposed to get is 20, but because of the readings you are making, you end up getting 25. What will happen? This 20 will not be accepted because the correct value is 25. But if you come, if this is part A, then part B, you come and use this 20, which is a wrong value, but you use it correctly. There is no penalty, and that's why I talked about consequential marking. Consequential, you don't penalize twice. Once you are penalized for a particular mistake, and maybe if I can borrow from mathematics, there is what we normally call propagation of errors, isn't it? It's a topic, propagation of errors. If I tell you to calculate, maybe I want you to give me the area of this duster. I expect you to come with a ruler, you measure the length, you measure the width. Okay? So if you make a mistake in measuring the length, so the area will be wrong. It will not be what I expected. But now, we shall look at it in terms of where did the mistake happen. The mistake happened at the point of measuring the length. So we shall penalize at that level, then the rest we move consequentially. Thank you.
Okay, let's have another set. Another set of 3. One is here.
So I'm asking on the reaction rate itself. When you're doing when we're doing the curve, the reaction rate curve, we draw it against the rate of reaction, which is the inverse of time. So at other times you can be told to draw against time, like directly. Do you still draw a straight line like the same way you draw a straight line when you're drawing it against the inverse of time?
Another question? You mean you have to write up? No question? No further question? Two more questions. Two more questions from the back. Okay, fine. Yeah. Yes, yes. Fine. So we can start. Okay.
Now, thank you. Just as I've said, what you do when you are drawing a graph depends on how the values are behaving. Because from our theory, we know that if a graph was a curve, then you, for example, if you draw the graph of, maybe it is, maybe you're measuring mass of something, maybe against time, isn't it? Then supposing the initial one was a smooth curve, isn't it? If you introduce the reciprocals, it becomes a straight line. So, this one here, when you draw these points, and remember, most of the data you get will be empirical data. Will be empirical data in the sense that it might also have, the examiner can deliberately introduce the error. Because when you are performing it in the laboratory, errors are bound to occur. That's what we know that. So somebody, maybe I've given you values. I'm expecting you to draw to get a smooth curve. But in the process of drawing, maybe you discover, maybe there's a value here, another one here, another one here, another one there, another one there, another one there, like that. So when you look at it, this one is suggesting that you get a curve. But now there's a value, if you include, the curve will not be smooth. The curve will not be smooth. So what you're supposed to do, you ignore that value, but leave the plot there. You just ignore the value and leave it there. Don't wrap. What some fellas do, after drawing it like this, you come with a rubber, erase, and you put it there. That one becomes wrong, isn't it? Because even whoever set that equation is aware, and you see that this one can be done to catch students who attempt to cheat, isn't it? From one another. Because if you just do it, this fella is aware that there is one value, can even just introduce that error. Yes, sir. So you ignore it. That's what I'm saying. When you look at how the points are behaving, if a point, if it's a linear relationship, when you look at the values, you'll just be able to see that this one is telling you it's a linear relationship. It's supposed to be a straight line. If it is a curve, you'll be able to tell that this one is a curve. You can just tell from how the points are behaving. Then, the aspect of extrapolation. The aspect of extrapolation, which I mentioned, because last year it was a major challenge. In fact, when you look at the report, one of the areas where candidates have difficulties is extrapolating. You have drawn a graph, and you're expected to use this graph to read a value that is not on the graph. What are you supposed to do? You're expected to extrapolate. So as you prepare, try to learn how to extrapolate different curves depending on the shape. Depending on the shape of the curve, know how to extrapolate it. So, if it's a straight line, make sure that you use a ruler. And if it's a curve, let it be a smooth curve. Have I answered you? Thank you.
Right. I think, do we have any one last question? One last question? Yes? Did I see a hand somewhere? Okay. Then I believe that there is.
Yeah, my question is organic chemistry 2. My question is on organic chemistry 2. How are salts formed? Salt formation. Salts.
Yes?
How are they formed?
How are they formed?
Saponification.
Now, okay. She's talking about saponification. Saponification. Now, what you're supposed to know about saponification, what we call a soap. A soap is a salt, isn't it? We know that when an acid reacts with a base, it forms a salt and water. So when you look at the manufacture of soap, it is manufactured from fatty acids, which are long chain carboxylic acids, alkanoic acids. So when you look at it as in a very simple way, if you have a long chain, we normally present that long chain using just an arc. Long chain, carbon, so many carbon atoms coming together. This one, what we are interested in is the acidic part, isn't it? So when you take this one and you react it with sodium hydroxide, this one is a typical neutralization reaction. And we have said, despite the fact that this alkanoic acid might have so many hydrogen atoms, it is only this one that is replaceable. So when you are writing whatever is formed, this one becomes RCOO. Instead of this hydrogen, you come and write NA. Then the hydrogen that is removed here comes to join with OH. To form a compound with 2 hydrogens and 1 oxygen. So we are just reacting an acid with a base. So that is neutralization to form a salt and water. And this salt, because it's a long chain, it is made up of a long chain hydrocarbon. So the salt, we call it sodium stearate, which is what? Which is called soap. Simple language. Sodium stearate, which is called soap. And the process is called saponification, because the word sapon means what? Soap. The word sapon means soap. So saponification refers to the formation of soap. Now, so this one here, you can look at the procedure. Look at the procedure. You can start with maybe with sodium hydroxide, isn't it? Then you start boiling, or an oil. You boil maybe for around 20 minutes. As you boil, you add a little drops of distilled water to make up for the evaporation. You know? So when it happens, you'll end up forming, you'll end up with a mixture of soap and glycerol. Then there's a step where we add sodium chloride so that it can reduce the solubility of soap in glycerol. Here I used a simple example of water, but you can also look at the procedure to reduce the solubility. So that process, somebody can ask you, why is sodium chloride added during the manufacture of soaps? You know, to reduce the solubility of soap in glycerol, or to make the soap to solidify. You know, because when the solubility reduces, the soap will settle down. What name is given to that process? Salting out. Salting out. So I want to believe that maybe you can take time, you just look at it explains very clearly how soap is manufactured. But maybe still on the soap, maybe what you're supposed to know is the difference between soap and soapless detergent, isn't it? We know the difference. So you know the difference in the structure, okay? So when you see an SO3 somewhere, NS, you know that one becomes a what? A soapless detergent. Now, when you are talking about the two, somebody can ask you, identify the one that is suitable for cleaning using hard water. So which one? The soapless detergents. Reason? Doesn't form scum, isn't it? That's an advantage. Okay? But the detergents, the soapless detergents also come with that disadvantage, isn't it? What is the disadvantage? The main one? Non-biodegradable. And that one leads to environmental pollution. Okay? What is the main advantage of soap over the detergents? Huh? The main advantage of soap. We have soap on one side, we have soapless detergent on the other one. So the detergent has got an advantage over soap, because it does not form scum with hard water. That's an advantage, isn't it? But it has also a disadvantage because it is non-biodegradable, which leads to environmental pollution. Okay? Now, what is the advantage of soap over soapless detergents? Yes. Huh? You can say it's biodegradable, isn't it? Yes, that's okay. What else? It is? That's what I wanted to hear. When you say it is cheap, that is very wrong, isn't it? When you say it is cheap, that is very... What are you supposed to say? It is cheaper, isn't it? Don't say cheap, because even 5 shillings to some other persons can say it's very little money, isn't it? But to another one, that's a lot of money. So when you are comparing, don't say it is cheap. You must say that it is cheaper, because you are comparing.